Hi there, everyone. Thank you very much for joining us today for our webinar with Test Force and NH Research on electric aircraft test approaches. We thank you for your attention and participation today, and if you have any feedback or other webinar topic suggestions for the future, then please let me know by chat or you can email us later at marketing@testforce.com. Just before we get started, I'd like to let everyone know that this webinar will be recorded and you'll be receiving an email afterwards with the recording, so you can go ahead and share it with anyone you think would be interested or rewatch it if you'd like. If you're interested in any of the other webinars we'll be hosting or to download any of the free resources we have available, such as white papers or application notes, please go ahead and visit testforce.com/academy and you'll find everything you need right there. If you have any questions during the webinar, then please make sure you ask them in the Q&A section. You can find that on the right side menu bar, and we'll be sure to get to all of your questions as we get to the end of the presentation with Daniel. And now I'd like to introduce Daniel McClelland from NH Research. His expertise are focused on electric vehicles, aerospace and defense, energy storage, and microgrid markets. Let's jump right in and talk about electric aircraft test approaches.
Hello, and welcome to our webinar about electric flight test solutions. Applications we'll cover today include the battery, propulsion system, and power electronics testing. My name is Daniel McClelland, and I'm presenting for you today from NH Research. I wanted to start out by saying thank you to our partners at TestForce for hosting this webinar. TestForce is our exclusive technical partner, local support, and distributor for NH Research products in Canada. I am the Eastern Regional Sales Manager for NH Research, and within that I cover Eastern Canada, the Eastern United States, and also Latin America. Within that territory, I have customers in each of those areas working on electric flight projects. It's a very exciting time to be working in this industry with a lot of growth and new emerging technologies coming to market. My favorite part of this job is working with my customers on the technical level to help them achieve their testing goals. Our agenda today is going to cover a few key topics. First, I'd like to do a quick introduction about NH Research to tell you a little bit about who we are and what it is that we do. Second, I'd like to review some market drivers that's really driving new test requirements in the industry from some of this new technology that our customers are working on. Lastly, I want to go into more detail on a technical level about modern testing requirements and new approaches for testing for the battery, propulsion system, traditional aircraft, and modern electric flight power electronics applications. So who is NH Research? NH Research is a small veteran-owned company located in Southern California. We've been in business for over 50 years in the power electronics test and measurement industry. Our motto today is to enable electrification. We do this by providing test equipment that has best-in-class performance for our customers to use in R&D applications for existing and future technologies. Our equipment is easy to use and has comprehensive software packages to integrate into your test systems. We provide modular and scalable test solutions. We help our customers reduce test time and also test safely. And lastly, we provide energy savings by using regenerative test equipment and recycling energy. Some of the world-class test solutions that NH Research provide are battery and fuel cell test systems, bidirectional DC sources, AC grid simulators for grid research, traditional AC and DC electronic loads or power supplies, and also power supply test systems. We also go beyond just being a hardware provider. We like to work with our customers after the hardware is delivered on the engineering level to make sure you're successful in your testing. The next agenda point is to talk about some trends in the marketplace that we've observed over the last few years for testing. Electrification is everywhere. It's driving new R&D in all different industries, whether that's the grid, transportation for commercial vehicles like passenger cars, or heavy-duty over-the-road trucks. We like to say planes, trains, and automobiles are all being worked on to include this new technology of electrification. Everybody's well aware of the new upcoming vehicles that are about to hit market from all the major vehicle manufacturers, but not that many people are aware of the research going on for electric flight. There's research being done on the commercial side for passenger jets and cargo planes, like you see on the left. And then there's also a wave of new vehicles that are in the eVTOL category for applications like electric air taxis and short duration helicopter type flights. One great example of a commercial product that is actually bringing this technology to market very soon is a project with Uber that's partnered with many of the manufacturers that you see on the screen here. They have a target of bringing an electric flying taxi to market as early as 2023. These look very futuristic, but we're going to see air taxis like this sooner than later. Some of these vehicles that you see on the screen are actually being prototyped and flown today, and in the development phase, they're using NH research projects to help with the R&D. Another great example of an electric flight project is with Raytheon Technologies, formerly known as Collins Aerospace. They have a hybrid flight project that is going to be Project 804, flying 804 miles using a hybrid electric propulsion platform. Collins Aerospace selected NH Research to provide a very high power megawatt plus DC power lab for testing any of the DC applications within the airplane. Test applications include the battery, the inverter, the propulsion system, and more. Electric flight poses many unique challenges and requirements for testing. On the R&D side, the battery needs to continue to grow in voltage while reducing weight and becoming more energy dense. For any flight application, weight is at a huge premium. Another system that's getting a lot of R&D focus is with the propulsion system. The motor drive is growing again in voltage, and power density is increasing at a rapid rate. They need to pack megawatt scale power into a very small package. Similar test applications exist between all forms of electrified transportation. The top areas include the battery, the propulsion system, and the power electronics. But even within electric flight applications, you see some difference in requirements for the product itself and the testing requirements as well. Commercial planes have much more weight to deal with, so they need high power on takeoff, but they also have longer flight plans where they need more energy for a longer duration. eVTOLs, on the other hand, for air taxis, have much more frequent takeoff and landing, but they're flying a shorter distance, so they will have many more high power events with the battery. Also, eVTOLs don't generate lift with wings, but they're much more like a helicopter where the motors need to be running at a higher power at all time, even in hover or cruise applications. To dive in more of a technical level on some of the test requirements, I want to first look at what some of the traditional aerospace testing applications are. NH Research gets its background working with the US military and many of the defense contractors out there on the market, going back 30+ years working with these partners with a heavy focus on aerospace testing. Top areas for testing for traditional aerospace applications include energy storage with batteries or capacitors, power electronics requirements for the propulsion system itself, although very different than a full electric platform. There are AC to DC and DC to DC converters on board airplanes. The high power system is traditionally an AC generator that needs to be tested. And then there's a whole slew of auxiliary loads, including relays, switches, contactors, actuators, and more that need to be tested, usually at a lower power, but can be tested with sources and loads. To now look at an electrified platform, one of the eVTOLs that we were talking about before, if you look at the top categories of testing, many of them remain very similar to the traditional aerospace applications. However, electric flight is driving things like voltage, power, and current much higher than the traditional applications. So now you have a high voltage, high power battery pack on board, typically a lithium pack. You have a propulsion system that now is usually in the megawatt scale, if not hundreds of kilowatts. You have a power distribution system that looks much different than before. There is still a DC to DC converter, although it's typically now bidirectional. And there's still traditional aerospace applications like electric actuators for the flaps. And there is also inverters for the motor drive and also inverters to connect to a traditional AC power system. The high voltage, high power battery pack remains one of the top areas of testing for electrified platforms. Modern battery testing brings about a number of challenges that cannot be effectively overcome by traditional test methods. Traditional battery testing used source load combinations, two separate instruments, a DC supply for charging and a DC load for discharging. That load sometimes was even just a large bank of resistors that was not even a programmable load, it was just a large power dump. This is still an approach that some people try and take today when they're building up their own battery test system. At the outset, it appears to be a very simple and easy approach, but there are a lot of drawbacks and hidden costs to this solution that are rarely understood up front. Last generation battery cyclers also struggle to meet the demands of modern battery testing. Past generation cyclers are very slow. They have a lot of output impedance, making them unable to perform fast transients. They tend to be noisy and they can lack accuracy as well. Let's take a look at some of the top objectives for modern battery testing. One of the key areas for testing batteries is recreating test profiles or waveforms on the physical battery using the battery cycler. On other electrified platforms, such as passenger vehicles with entities like the SAE, they dictate test profiles that need to be run for safety purposes on the battery before it's validated to be used in application. There's agencies today working on the same effort for electric flight batteries. Some of those include people like the FAA. Electric flight is also still heavily in the prototype and simulation phase. Many of these vehicles don't yet exist outside of a computer, but you want to start doing R&D and development on some of the subsystems like the battery itself. So modern equipment should be able to take simulated profiles and simulated waveforms and recreate those on the physical battery. Lastly, modern equipment needs to be very fast, precise, and accurate to be able to successfully recreate these profiles. And there should be tools built in to scale and adapt these test routines to different battery sizes, power levels, C rates, and even different battery technologies. The battery management system is also a large challenge of modern testing. Lithium battery packs include a BMS on board, or battery management system, that monitors the cell voltage, cell temperature, closes contactors, and communicates with other systems within the plane. This BMS system needs to be interfaced with within your testing environment. One of the major goals for testing the BMS is to use this data to validate the battery's performance. You want to see what's happening inside while you're performing that large current discharge, for example. And another area is to validate this BMS itself. This BMS also needs to be tested. Using external data acquisition in conjunction with a battery cycler, you can validate those cell temperature readings and cell voltage readings, among other things. Modern battery testing is a very complex environment. Modern systems need to be flexible and easy to integrate with other instruments outside of just the battery cycler. They need to be easy to use to provide fast and accurate testing to accomplish these new R&D test goals. And lastly, safety is a large concern when dealing with a high-power battery pack. Modern systems should have layers of safety. We'll go into a little bit more detail about that on a later slide. NH Research approach to modern battery testing is to use a high-performance battery cycler that now, instead of being a source-load combination, this instrument is capable of syncing and sourcing on a single channel connecting to the battery. This has built-in safety measures, fast transient capabilities using silicon carbide topology, and it's modular and scalable by design. Modern power electronics are being used to develop these new motor drives and inverter technologies. Modern lithium battery packs can provide power at an extremely fast rate. Your test solutions need to be able to keep up with the performance of the application. A traditional DC supply has a lot of output capacitance, which is great for regulating a voltage at steady state, but not so good for performing fast transients. These fast transients need to be done when recreating some of those drive cycles, for example. Using modern power electronics within the test equipment itself, you're now capable of performing very fast transients. Instead of 20 milliseconds for 10 to 90 rise time, you now achieve a sub-millisecond rise time for full power transients. Electric flight applications are changing all the time in power level, voltage, and configuration. You don't want to purchase a piece of test equipment specific for one application and then next week find out that you don't have enough power. With NH Research Solutions, we prioritize modularity and scalability. With 2 battery cyclers from NH Research, you now have two 100 kilowatt channels. You can also run those in parallel to achieve 200 kilowatts max power. If later on you find out that you're running at a higher power level with a future battery design, you simply add a 3rd cabinet and now you have complete control of your test environment, whether that's 300 kilowatt channels or as high as a single 300 kilowatt channel. This method applies to all power levels from 100 kilowatt up to 2.4 megawatt. This is a system that will grow with you over time. NH Research also provides open source, flexible, and easy to use software packages. For control, we have easy to use and easy to understand front touch panels that display what's happening with the equipment and also gives the user an easy interface for manual control. We also have remote control capability over Ethernet to bring the same functionality to a remote control station, whether that's a laptop or a desktop PC. We also provide drivers for Windows-based programming such as C++ or Python is a very common example. And we also provide complete LabVIEW driver sets ready to use with example programs as well. Lastly, we do have our own test executive solution. If you're not a programming expert, but you want to get into some automation for your battery testing, we do have a system software that has a lot of the hard development already done. It takes a very complex programming job and makes it into a much more easy to use environment. So we give the customer a lot of different options for how to control our equipment. Going back to the topic of safety, again, with batteries, you can never be too safe. Everybody knows about software safeties. Software safeties have a couple different levels. You have the measurement that's going on with a feedback loop of monitoring the actual performance and reacting on a software level. That tends to be a slower rate of control. Adding more layers to this, you now add hardware safeties, where safeties can be programmed directly into the test instrument itself. These hardware safeties are reacting on a much faster rate on the microsecond level instead of communication delay of milliseconds over software. When you start to see voltage or current transients go out of range, you want that high-speed response of programmable hardware safeties. We also provide external interlocks that can be wired in for things like lockout tagout procedures, as well as emergency power off buttons, e-stop buttons. Lastly, as best practice, we provide a communication watchdog. Software safeties are only as good as that communication link. If you ever dropped out of communication, or let's say your software controller, like your laptop, goes into a Windows update without plan, you've now lost your software safeties. So having these multiple layers of backup is very key for a safe testing environment. The NH Research solution for battery testing is either our 9200 or our 9300 system. They're both modular and scalable solutions that cover low power to high power. They give a very wide operating envelope per module, a wide range of constant power usage. The 9200 is a 12 kilowatt building block that can go up to hundreds of kilowatts, or the 9300 is now a 100 kilowatt building block that goes all the way up to 2.4 megawatt. They both are built on the latest silicon carbide topology for very fast response times. Both systems provide full power transients in the sub-millisecond speed range. They both have advanced built-in measurements, simplifying your test setup and eliminating things like scopes and data acquisition that need to be controlled and logged externally. These systems have built-in measurement and built-in logging capability to eliminate those external devices. They both include multiple layers of safety, including those hardware safeties, interlocks, and emergency stops. They both provide software and control mechanisms that are flexible and very easy to integrate into your test setup. And lastly, another topic that we'll get into a little bit later, they both can act as battery emulators as well. These are the same equipment that we use to cycle batteries, can also be used to test any battery connected device within the vehicle. These systems give programming flexibility for constant current, constant voltage, constant power, and/or constant resistance. You can run any mixture of these to recreate any test profile that needs to be run. As I mentioned before, battery testing starts out looking like a very simple application that is a device that just needs to be charged up and discharged. You quickly learn that battery testing is much more complex. There's communication that needs to occur with the battery to monitor that BMS, and also communication with other devices. Very commonly, batteries need to be run in temperature chambers to cycle the temperature that coincides with battery cycling profiles that's run at the same time. There's also automation that needs to be done with relays, external I/O, maybe even PWM drivers for applications within the system. Usually, people want external data acquisition for measuring things like cell voltage and temperature to validate that battery BMS. And lastly, there might be some external DC loads and DC supplies that need to be applied separately from the battery cycler itself. Batteries typically need a 12 volt or some other voltage supply to power up the pack, external from the power connection itself. As you can see, a very simple seeming application quickly grows to a very complex environment, and the battery cycler needs to be built with this test method in mind. We provide the software and the hardware solutions, and also a test executive that can help you build up a battery system that's very comprehensive and very complex, but can be set up very quickly and help you achieve your testing goals. The next topic I want to get into is the electric propulsion system. It's an equally large challenge to the battery and one that's seeing a lot of R&D for electric flight. The electric propulsion system for flight applications takes a few different forms. There's parallel and series hybrid setups where you still have a gas-powered turbine also driving the propeller. And then there's applications like the eVTOL or maybe a drone where it's purely electric. Two different applications, but as you can see, there's common systems between each one. There's a battery, an inverter, and a motor. The good news is the same equipment that we just reviewed for battery testing is also the equipment that we recommend for battery emulation for testing the propulsion system. Battery emulation is a new concept for a lot of people in the industry. This is a new technology that we've brought to market. And the reason why you'd use a battery emulator is to more closely match real-world conditions in your test environment. A battery emulator, you're now capable of programming not only a voltage, but also giving that voltage an associated equivalent series resistance like your battery pack would have. And now when the current flows in or out of the battery, you now see that associated rise or fall in the bus voltage like you would expect with a battery pack. With a battery emulator, you also get much more repeatable test results. A battery pack itself is a non-ideal, non-precision device. The battery's performance varies with age, with temperature, and with state of charge. With a battery emulator, you now have a precision test instrument that you're able to get repeatable test results no matter the time of day, how often you test, or the temperature in the room. The battery pack, as we talked before, also poses a large safety risk within your test environment. The battery is a risk not only to the personnel, but also the equipment in the room. A high power battery pack can fail catastrophically and it can take out an entire room worth of equipment. A battery emulator removes that safety risk from your lab environment. And lastly, one of the largest benefits for a battery emulator is you've now dramatically reduced your testing time. With a physical battery, you need to condition that battery before you're able to perform your testing. You need to either charge it up or discharge it so you can hit your different states of charge. The other aspect that a battery emulator allows you to do is now you can test things like over power, over voltage, under voltage, test cases where it would damage a physical battery and you don't want to damage your battery in testing, but you also should know what happens in application when you do have a battery fault during flight. This slide shows a comparison between an actual test that we ran in our lab on a 48-volt battery pack and recreating that test using an NHR battery emulator. On the left side, we had the 48-volt battery being cycled by NHR battery cyclers. And on the right side, we were cycling our battery emulator, again, using our battery cycler. If you overlay these tests, you can now see that the data overlays very, very closely. A battery emulator can provide extremely close to real-world results in your lab while still getting all of the benefits of using a piece of test equipment versus a physical battery. Electric propulsion involves three key areas. You have the electric motor, the inverter or the motor drive, and the high voltage battery pack. We've just talked about all the reasons why you'd want to eliminate that battery from testing. So for these next slides, let's assume that you're using a battery emulator during testing. This leads to three key types of propulsion test stands. You have a single-ended DC bus, a common DC bus, or an isolated DC bus. Let's take a closer look at these three test stands. The first setup is a single-ended DC bus. What this means is you have a battery emulator that's driving your motor drive, which is in turn spinning your motor. That motor is running into a physical load. This test setup is very common for the aerospace industry because you already have a load there with the propeller. When the motor spins, it drives the prop, and you have that wind resistance against the propeller. Automotive applications also use this by running the motor into a water break or some other physical load for testing. Some of the benefits for this test setup is that it's very simple and easy to set up. And you can also characterize that DC link because you have no other interference with the DC side of the inverter. You can now measure waveforms and characterize the response of that DC side. An evolution of the single-ended DC bus is to now set up a common DC bus. This is done by setting up two motors in a back-to-back configuration. On the left side, you have your test motor, and on the right side, you have your load. The battery emulator is now maintaining a common DC bus between the two motor drives. When the load is being spun, it's generating an output current which is being fed back into the drive motor, and you're now recycling the power used during testing. With a high efficiency DC bus regulated by our battery emulator, you've now reduced the cost of testing by over 90%. This is reducing your power usage in the facility, reducing the heat in your lab, and also reducing the cost of testing. One thing to note is you do lose the ability to characterize that DC link of your test motor drive. This is because when the regen is happening, it's happening on that common DC bus, and you're feeding that current back into the inverter. A further evolution of the common DC bus platform is to now move to an isolated DC bus. This is done by running two separate battery emulators into the two separate inverters. This is still a regenerative test stand, getting all the benefits of regenerative equipment, reducing cost, heat, and power demand from the facility, but now you do regain that true test on the DC link of your motor drive. You're able to characterize that DC performance and also get the benefits of regenerative test equipment. With modular equipment from NH Research, you now have your choice between a single-ended DC bus, a common DC bus, or an isolated DC bus. Because the equipment is modular and reconfigurable, you can mix and match and change between these different test setups depending on your different test goals. To summarize the benefits of using battery emulation for propulsion testing, bidirectional equipment eliminates the risk of back EMF and reduces the amount of instruments that you need to control during testing. Battery emulators allow for high performance transients and for recreating real world conditions using that series resistance. You're also able to get that fast transient to characterize high speed events. Wide operating ranges allow you to apply the same test equipment across a wide range of applications. Our emulators cover voltages up to 1200 volts and 2.4 megawatts. Flexible and scalable equipment allows you to reconfigure your test stand and grow it over time. And hardware safety features and eliminating that battery during testing means you're eliminating risk from your test environment. The last category I want to cover is traditional aircraft power electronics and also modern electrified platforms. PDUs and power conversion testing goes back to the roots of our company at NH Research. Whether it's an AC to DC, DC to DC, or some other multi-input, multi-output box that needs to be tested, NH Research has the programmable sources and loads required for testing all of these test applications. Also, with the newer test equipment, such as our battery emulators and 4-quadrant AC loads, you can do things like motor emulation and also test bidirectional devices, such as DC to DC converters or bidirectional inverter applications. NH Research DC loads are some of the best in the industry for high speed. We can provide transients and waveforms on the kilohertz scale. As you can see in this shot here, we can recreate very complex test profiles with the stair step, or very fast pulses, or things like notches or triangle wave shapes. We provide many different modes for programming, including constant current, constant resistance, constant power, and constant voltage. This allows you to emulate all different types of loading cases in the real world. We also have some of the highest accuracy in both set and measurement, as well as multiple ranges on the same device to apply to many different test cases. Our power supply test systems utilize our own test equipment, but now come in a commercial off-the-shelf test system solution package. This not only includes the test instruments themselves, but also a test executive software package that is easy to use and provides very quick time to test. Mixing multiple different test instruments allows for a very wide configuration flexibility. Our software package has a library of pre-developed templates that are easy to use and don't require as much programming knowledge to build up a very complex test routine. These systems are standard, using standard equipment, but are built to meet customer specifications. We can provide simple systems with single input, single output, or very complex systems with multiple inputs and multiple outputs. One of the largest areas of value for these systems is a significant reduction in time to test. Compared to going through a third party that's custom built or building up your own system on site, these pre-developed solutions that are standard off the shelf are already developed and ready to go when delivered. NH Research also provides training packages and support packages for things like calibration and service contracts over the years. NH Research system solutions are appropriate for R&D characterization, production, and repair depots. The 9430 is the last instrument that I want to talk to you about. Our 4-quadrant AC load was released in direct response to the test requirements for the aerospace industry. The 9430 is an AC load that's scalable up to 96 kilowatt. It's also regenerative with over 90% energy efficiency. It can be run in a single phase, split phase, or 3-phase mode up to 880 hertz, or it can be run as a DC load as well. The key thing about the 4-quadrant 9430 AC load is that it's truly able to emulate inductive or capacitive loads without using passive components. This allows for emulating applications such as motor emulation or testing to industry standards that require power factor shift without using a high crest factor. The 4-quadrant AC load can run at a continuous 0.85 or a 0.7 power factor without switching in inductors or capacitors. To give a demonstration of that power factor phase shift, you can see all different operating points here. The instrument itself is able to run from a -1 to a +1 power factor, going from unity sourcing to unity sinking. As seen on these waveforms, there is no crest factor estimation of a power factor load. This is a true phase displacement of the current from the voltage. This allows you to simulate any power factor at any current. If you do want to generate dirty waveforms, we give you a lot of programmable tools to accomplish those as well. You can program the usual high crest factor, asymmetrical loads. We give you a harmonics generation tool and a macro editor that allows for fast playback of transient conditions such as motor inrush with a crest factor that settles into a unity condition. That concludes the technical content that I wanted to review today. I wanted to make note that all of this content is available on our website, nhresearch.com. You can view other webinars that we've done covering other technical content. You can visit our page for electric aircraft test solutions. You can read an app note about battery emulation. And if you have any testing that you need to do that's upcoming or existing, I urge you to reach out to us over phone or right into our website to schedule a conference call to review your application with us. Thank you again for attending. Again, my name is Daniel McClelland. My contact information is here on the screen. And I believe we're going to now open this up to questions. I'll pass it back over to our host. Thank you very much.
Great. Thank you very much, Daniel, for presenting today and for the informative, detailed webinar. And I'd also like to say thanks to all of our attendees who made the time to sit in with us today and for your participation in asking questions. So we're about to get to the Q&A section. I did also just want to remind everyone, in case you missed it at the beginning, that this webinar was recorded. So I'll send out an email with a copy of the recording in the next day or so. I'm also about to open up a poll that will keep open during the Q&A session so that you can fill that in at your convenience. It's just a few multiple choice questions, and if you can fill those in with any additional comments you might have, we'd really appreciate your feedback. So I've just opened it up now. You should see it pop up on your screen. In the meantime, we did have a question come in from one of our participants today. So here he's wondering what kind of battery cooling and temperature control is being applied to the battery pack.
Good question. We're seeing a lot of different technologies out there. Most commonly, what we're seeing today is a glycol-based coolant. That's very common for automotive. You know, it's like the cooling system in your radiator today. That's being pumped usually through the battery, through cooling plates, and in testing, there are some people that we've used in the past that make those glycol temperature conditioners. And those are things that can interface with our test executive as well. So if you want to emulate those temperature conditions through the cooling system, you could do that as well.
All right, that's great. And so, sorry about that, I'm just reading through the questions here. So we do have another question. How can you reduce the overall testing time? Is there an easy way to do that when designing an electric aircraft?
Sure, good question. A lot of our focus has been on our new instruments for sure to help our customers reduce their testing time. And some of the biggest ways that we're doing that is through the flexible and modular nature of the equipment itself. We, especially on the DC side, a good example is that Collins Aerospace project where they have that entire DC lab. They're able to test any of the DC applications within that lab. So the same test setup, the same test equipment, you make one purchase and now you're able to test the battery, things like the propulsion system and all the power converters as well, the DC to DC converters or the inverters. So just having that one system that's so flexible. And then also, instead of just focusing on component level testing, you're also able to do system level testing by running those 9300s or 9200s in parallel. You can do the higher power system level test where you're testing multiple components at the same time. Some of the other things I would say for reducing time would be the built-in measurement and built-in safeties. That reduces the time required to build up that test system. And then lastly, we've got drivers and example programs that we can give you as well to help you reduce that development time.
Okay, that's great. We have another question here, but just a reminder, you guys can, any of the attendees can put your questions into either the chat box or the Q&A section. Okay, so we have one of our attendees who's wondering, who, in your opinion, would make the best batteries for engines? So maybe something the lightest and powerful. Or have you come across that at all, Daniel?
Sure. There's a number of suppliers out there today. I would say it might be encroaching on some NDA type agreements that we've got out there to name any specific manufacturers because they are partnered with some of the vehicle manufacturers that we're working with. But I would say that the ones that people are choosing are there's both startup companies that are producing aerospace batteries and then also people that have been in the industry for a very long time. With aerospace, of course, it's a very critical application, and a lot of the military and the aerospace suppliers that are in the market today are the same ones that are tackling this newer technology. So I'd look for military type suppliers. As far as technology goes, the vehicles that are flying today are almost guaranteed to be using a lithium-ion battery, something that exists today. There definitely is a lot of research going on, things like solid state or semi-solid lithium technology, or maybe some other chemistries. But for something that you'd be able to work on today and actually purchase, put together, and get in the air, that would be a lithium-ion pack.
And just to add on to that question, he's wondering if it would be Li or OXi, lithium or oxy?
Sure, I covered that a little bit just now. Like I said, for things that are going to actually be flying today, I've seen lithium packs being used just because of availability and the expertise in the technology. But definitely there is a lot of R&D going on. I don't think there's anybody in the market today that's saying that we have all the answers or all the technology needed to make electric flight viable right now. So there's people that are pushing the boundaries and setting the goals. People like Uber that's putting the money up with a target and a deadline of 2023. And there's flights that are happening right now with existing technology. But there's the research targets that are out there that everybody knows that they need to keep pushing the boundaries to be able to make this electric flight happen.
Okay, great, thank you. Now, yep, that's great. Glad we answered your question there. So do your battery emulators also test fuel cells?
Good question. Yes, the flight vehicles we've seen that have fuel cells on board, typically it's going to be something like a drone, like an unmanned flight, or a satellite maybe would have a small fuel cell on board. Our battery cyclers, yes, they can test fuel cells as well. Our battery cyclers, they can operate purely in a load mode, like just a regenerative DC load. And then also, if those fuel cells, sometimes they are connecting on the front end to some form of energy storage, like a capacitor or a battery, or maybe a DC bus where that equivalent resistance is known on that bus. You'd be able to use that battery emulation mode to accept that power from the fuel cell and then also emulate that rise or the fall of the bus voltage. The key thing with a battery emulator is it now allows you to connect multiple devices to that same DC bus to do that system level test. And the satellite guys especially like this because they have not only things like batteries and fuel cells on that bus, but they also have solar for solar emulation, and also power distribution to be charging batteries or powering different loads like the actuators.
Okay, and in your opinion, Daniel, do you think we will start to see hydrogen fuel cells play a large role in the future of electric flight?
Fuel cells, I think it is going to be important in applications like drones and like satellites. As far as flight vehicles that people are actually going to ride, or maybe larger commercial flights, I'm not so sure. The weight and the packaging of a fuel cell right now is probably larger than what can be accomplished with a battery technology. But for fuel cells, definitely they have a place for stationary power, and also the larger over-the-road trucks or the heavy-duty bus applications. That's really where we're seeing a lot of development for fuel cells. But the good thing about electrified platforms is there's a lot of crossover between different applications. So R&D that's happening today for things like buses or trucks would definitely cross over to flight vehicles. So if there's a breakthrough in one area, that can be easily applied to electric flight in the future.
Okay, we do have another participant who's wondering, how does regen work? To be able to use the regen function, I would need to add external electrical equipment, such as bidirectional transformer, synchronizer, to be able to regen back to the grid.
Sure, good question. So our equipment is built from the ground up to be regenerative. If you imagine the connection that's made to the facility is very, very close to what you would see with a solar inverter, for example. So imagine if you put solar on your building, it would be a very similar process. The panels are generating electricity, it's being fed through an inverter, and it's helping power the building, offsetting the loads of the building. Our equipment is very similar. It's got multiple power conversion stages within the DC instrument itself, and that final stage that connects to the building is an AC to DC inverter stage. We have ourselves built-in isolation, so there's no isolation transformer required on the external side, and we also build in things that ensure that the power remains very clean. So we have a very good power factor, 99% or better power factor on the AC side. And so for us, the only requirement is having enough power to power the instrument. For 100 kilowatt, you would need at least 100 kilowatt service. And our input voltage is typically a 480 volt input voltage. So we are compatible with auto transformers, if a different voltage is present at the facility. But again, all of the isolation, all of the difficult part is handled by the instrument itself.
All right, perfect. We'll do one more question and then see if we get any more coming in. So do you test the propulsion the same way for a fuel cell electric plane?
Okay, so the electric platforms are generally very similar across all different types. So whether it's a battery power source or a fuel cell power source, it kind of goes back to the slide where we were looking at the hybrid and the full electric platform. Even in the hybrid applications, you have the similar building blocks. So the propulsion system is typically made up of an energy source, whether that's a battery or a fuel cell. And even with the fuel cells, sometimes you have a fuel cell and a battery. But then the propulsion system itself would be an inverter stage or the motor drive, and then a motor that would actually turn the propeller. So I would say yes, the propulsion system itself would not really care if it's being powered by a battery or a fuel cell. And yes, our equipment can perform both battery emulation, or that can be adapted to a fuel cell emulation as well. We have a very robust tool for programming both that voltage and the series resistance to be able to replicate different power profiles being generated by different technologies.
Okay. If we do get any more questions, I can leave the chat open for a little bit longer. We do have a few more minutes left, but yeah, I just asked one of our participants to clarify a little bit. So if there isn't enough time, then we'll get back to you directly, and I can get Daniel in touch with you to answer any additional questions you might have. So thanks again, everybody, for joining us today. If any questions do come up later, like I mentioned, don't hesitate to reply to my email. You can also send us a message to marketing@testforce.com, and we'll get back to you with the answers or put you in touch with Daniel. And again, Daniel, thank you very much for your time today. We appreciate it.
Thank you, Marla.
And you know what? One more good question did just come in.
Okay.
If you don't mind, we'll
Yeah,
try and answer it here. It may be helpful for others as well. You mentioned capacitor storage for fuel cells.
Mm-hmm.
Is there significant advantages this can offer over lithium-ion packs?
Sure. So the fuel cells themselves are more of a steady state type energy source compared to like a capacitor or a battery that can provide very fast transients in both current, providing current and also power. Typically, when you're connecting to a piece of power electronics like a motor drive, it doesn't really care, so long as you have enough potential, it doesn't really care what the voltage is. What that motor drive is looking for is a constant power type power coming from the energy source. So with a fuel cell, if you have a very fast transient, let's say you go from 0 to full power, you might collapse the voltage on the output of the fuel cell. You're pulling more energy from it than it can provide at a high speed. So you would need either a capacitor or a battery on that front end to be able to dampen those transients and cover those high speed, high power transient conditions. Whether that's a capacitor or a lithium battery, that comes down to the size of the fuel cell and how quickly it can respond. Obviously, a capacitor is not going to have as much energy storage, but it can still cover those very fast transients. So I wouldn't say there's really an advantage to one versus the other. The capacitor can probably be a little bit more energy dense, but it can't hold as much energy and provide as much energy for as long of a period of time.
Perfect. That's great. So that was all of the questions that we had come in through the chat. So
okay.
Yeah, so thanks, Daniel, again, and everybody. I hope that you stay safe and have a nice day, and we'll look forward to hearing from you in the future.
All right, great. Thank you very much.
Take care. Thank you. Bye-bye.